Imagine you're holding a person up in the air, and suddenly you let go. On Earth, they would fall to the ground. But what if you were somewhere with no gravity? As soon as you let go, there is no external force acting on the person, and let's watch what happens. So they start to let go. There's nothing pulling the person, and they remain at rest just like before. Let's see the same concept with spheres. If we let them go in outer space where there's no gravity, they just remain there. But as soon as we exert this external force, they start moving. Right there, they're just suspended in the air because nothing is pulling. The net force is 0. But as soon as we apply a net force, they accelerate. Now look at this. Once the ball begins to move and the force ceases, once it's in motion, is it going to eventually stop? Let's watch and see what happens. It moves at a constant speed in a straight line. Let's see another example of that. When you set an object in motion, if it no longer feels other forces, it will just keep moving at a constant speed in a straight line. So they're going to flip this coin out in outer space, and it just keeps going at a straight line with constant speed. This can be a strange idea that objects continue their motion until a force brings them to rest, or until a force speeds them up. So if we have a person in a car, and the car suddenly slams on the brakes, well, yeah, the car feels a force that brings it to rest. But the person may not immediately feel that force, which is why you jerk forward. Let's watch. You continue traveling forward for some time, and we wear a seatbelt so that we don't continue all the way to the windshield. So what's happening? You're in motion inside the car, and when the car suddenly stops, you tend to continue your motion. You move in a straight line with constant speed until the seatbelt exerts a force and slows you down. Let's turn to page 7 in our notes and write this down now. Newton's first law states that objects at rest remain at rest, and objects in motion will move in a straight line with constant velocity, or speed, we could say, unless they are acted upon by an external unbalanced force. This was a revolutionary view because before Newton, people didn't think this. They thought something else happened. Before Newton's time, people thought that objects in motion all will eventually slow down. They eventually stop. They lose their steam. And Newton came along and said, no, they will not stop unless a force, like friction, brings them to rest. On the next page, we call this inertia, the law of inertia, because inertia is the property of mass to stay at rest or continue moving in a straight line at constant speed. Consider a giant elephant, and then on the other hand, we have a tiny little fly. Which one has more mass? The elephant. Which one has more inertia? The elephant. Inertia comes from our mass. The more mass, the greater the inertia. The less mass, the less the inertia. So which one of these has more tendency to stay at rest? The elephant, because inertia is the tendency to stay at rest. Which one of these has more tendency to continue its motion? The elephant, because it has more mass and inertia. That's intuitive, because if the elephant is moving at you at 5 meters per second, and so is the fly, it's a lot easier to stop the elephant, and it's a lot harder to stop the elephant and easier to stop the fly. The fly has less inertia, less tendency to keep moving in a straight line. So consider these 4 objects. The arrows show us the forces that they feel. Now, these forces, maybe they're gravity forces, or maybe they're normal forces or friction. We really don't know. All we know is how many forces are pushing or pulling the object, and which way. So this object feels 4 different pulls or pushes, but these only feel 2 individual forces. This thing is not getting pulled or pushed at all by any object. What do you notice that's the same about all 4 objects? The net force is 0 for every single one. If we look at this guy, and if we were to add the y-axis forces, this is exactly as long as the down arrow, and they would add to 0. They cancel out. If we add the x-axis forces, those cancel. Same in the other cases. And there's nothing to add, so by definition, the net force is 0. If I ask the question, what's the object doing? The only way to answer is using Newton's first law. If the net force is 0, if there's no unbalanced force, the object keeps doing what it's doing. If the object is moving, and we can't tell if we see only forces, if it's moving, then it moves in a straight line with constant speed, just like the coin that was flicked. If we have the object at rest, it will just stay at rest because there's no force, there's no net force changing its motion. That's what Newton's first law says. Net forces change the motion. They slow or speed the object, they start moving the object. And if you have no net force, you will continue moving or you will continue staying at rest. Now on page 11 of our notes, let's copy down what Newton's second law states. Essentially, the second law says that a net force changes the motion, causes acceleration. That's an informal way to phrase Newton's second law. Here's the official way. An object's acceleration depends directly on its net force and varies inversely with its mass. That sounds kind of fancy, but here's what that equation really looks like. Acceleration is equal to net force divided by mass. In other words, if you have a bigger mass, you will tend to have less acceleration, like the elephant. And if you feel a bigger net force, you will tend to accelerate more. We typically take this equation and we rewrite it in we cross multiply by mass, and we rewrite it to say net force is equal to mass times acceleration. Those are vectors, so F net and A point in the same direction. If you accelerate like this, we could multiply that by the scalar mass, which maybe makes the vector longer, and here's what your net force looks like. It's the same value, it's just scaled up according to the mass, this scalar. The direction has not changed. So if we ask the question, what are all of these objects doing? Because they all have the same motion. So if we look at these three objects and we say, what is every single one doing? Well, again, we don't know if the object is already moving or if it's currently at rest. All we see are the forces. But if we look at the forces, there's something similar for every single one. On the first object, the up force cancels the down force perfectly. What about the x forces? Well, this guy will cancel out some of F2, but there will be a net force remaining. That's how much doesn't cancel. On the second object, again, the y-axis cancels. Those forces are equal, but they're opposite values, so they add to 0. And then there's this F3 that doesn't cancel. And down here, there's only a single force, which points to the right. In all three cases, the object feels a rightward net force. And so in all three cases, what can we say about the motion? The object is accelerating to the right. Consider this question then. An object is moving to the right at constant velocity. Which diagram below could show the forces on the object? Wait a second, don't be fooled. It's not this or this or this. Why? All of those objects, all three, have an unbalanced force. Here's the net force. Here, the net force, if we added those two arrows together, the net force would be at an angle. But there's a net force. Here, there's a net force. Why can't this object have a net force? Because it has constant velocity. Net forces cause acceleration. This object isn't accelerating, so it's not any of those. Which one of Newton's laws talks about constant velocity? It's Newton's first law, which says your velocity is constant if there's no net force. These are the correct answer because all show a net force of 0. And hence, every single object will maintain the same motion, which in this case is moving to the right. How about this question? An object is accelerating to the left. Which diagram could show the forces that the object feels? Wait a second. If it's accelerating to the left, then it must feel a leftward net force. That's what Newton's second law says. Acceleration comes from net force. So which of these objects have a leftward net force? It's not this one because those cancel. It's not this one because that feels a rightward net force. Here again, the object has canceling of the forces. And then we look at the rest. Is this a leftward net force? Yes, it is. How about this? Yes, because the up and down forces cancel. And then this rightward force will cancel out some of the leftward, but there's going to be some left over too. So this rightward force cancels out some of the leftward, but on the whole, the net still points to the left. If we look at this again, we have another scenario with a leftward net force. This net force wouldn't point to the left, it would point rightward and upward. This one doesn't point left either.